Welcome to this course on radiative heat transfer, the natural phenomenon through which heat is transferred through electromagnetic radiation. This course is divided into chapters, so feel free to jump to the part you are most interested into, if you don't want to follow the whole course. Let's start with an introduction on the concept of radiation, and let's have a look at the first physical laws that concern this phenomenon. Radiative heat transfer is the only heat transfer mechanism which does not need a medium, since electromagnetic waves can propagate also in a vacuum. According to classical electrodynamics, electromagnetic waves propagate through space carrying energy along their path. These waves are characterized by their frequency nu and their wave vector k. This theory can describe propagation from a source to a receiver, but fails to describe emission phenomena and the interaction between electromagnetic waves and matter. While, according to quantum mechanics, energy is emitted and interacts by means of entities called photons, each characterized by an individual energy EPH and a momentum p. Propagation is explained in terms of photonic flow, and when a photon interacts with matter its energy is transferred. Of course, for both the theories to be accurate, there must exist equivalency relationships between these two theories. These relationships are Planck's law and de Broglie's relationship. Planck's law states that a photon energy is proportional to its wave frequency by a factor h, which is the Planck's constant. De Broglie's relationship states that the momentum vector has the same direction of the wave vector, and its intensity is proportional to the intensity of the wave vector by a factor h over 2 pi. Other quantities characterizing propagation are the speed of propagation, which is equal to lambda times nu, where lambda is the wavelength of the electromagnetic wave, and the refractive index, which is the ratio between the speed of propagation in a vacuum and the speed of propagation in a medium. Now let's translate what we just learned in terms of heat transfer. Heat transfer radiation is produced by the so-called thermally stimulated emission. When atoms are thermally stimulated, they reach a higher energy level, which brings those atoms into a less stable state. In order to reach a higher stability, atoms give out their energy by emitting photons. There are different waves in which atoms can emit photons, and depending on the way of emission, the energy of their photons changes. So, electromagnetic waves do not have a single frequency or wavelength, but their wavelength covers a range of wavelengths, called electromagnetic spectrum. The fraction of this spectrum, which corresponds to thermal radiation, is the thermal radiation spectrum. Conventionally, it covers a range from 0.1 micrometers to 1000 micrometers. This is not true, but, as we will discover shortly, it is a reasonable approximation. To understand why such approximation on the thermal radiation spectrum holds, we can use the Wien's displacement law. This law states that the product between the emission peak wavelength, or the wavelength corresponding to the most intense emission of a body, and the temperature of that body, is constant, and it is equal to 2898 micrometers Kelvin. The range of wavelengths and temperatures involved is shown in the plot. On the top left of this slide, the temperature corresponding to 0.1 micrometers is about 29,000 Kelvin, which is above the temperature of the Sun's surface, while the temperature corresponding to 1000 micrometers, which is close to the wavelength of the cosmic microwave background radiation, is about 2.9 Kelvin, which is an extremely low temperature, since it is quite unlikely to have temperatures outside of this range. The assumption made on the thermal radiation spectrum is reasonable. Therefore, as the figure below shows, the thermal radiation covers the whole infrared and visible ranges, and part of the ultraviolet range. Since we are dealing with electromagnetic waves, which propagate in every direction, it is useful to use spherical coordinates. Consider this figure. A point P is placed at the origin of the x, y and z axis. A point Q is placed at a distance r from point P. This distance is called radius and is one of the three spherical coordinates. The remaining two are the angles theta and phi. The angle theta is the angle between r and the z-axis, and it is called zenith. The angle phi is the angle-formed segment PQ', and the x-axis, where Q' is the projection of Q on the xy plane, and it is called azimuth. Now consider two infinitesimal angular displacements, d theta and d phi. The arc QR is equal to r d theta, and the segment PQ', which is equal to TQ, is r sine theta. The swept arc QS is equal to r sine theta d phi. So, the swept area DAN is equal to r squared sine theta d phi. The solid angle, in spherical coordinates, is defined as the area DAN over the squared radius, and is thus equal to sine theta d phi. If we integrate this angle over the hemisphere lying on the xy plane, the obtained angle is 2 pi, while the solid angle corresponding to the whole sphere, which is the double of the hemisphere angle, is 4 pi. Now, let's use what we just learned to define our first radiation quantity. The intensity of radiation. Consider the same system used before for the explanation of spherical coordinates, but this time the point P is a radiation emitting source. As before, dAn and d omega are the infinitesimal area and the infinitesimal solid angle being crossed by radiation. Let's call dE the energy transported by radiation in an infinitesimal time interval dt. And let's call d lambda an infinitesimal wavelengths interval of the radiation. The intensity of radiation, I omega lambda, is then defined as dE over dt, d lambda, dAn, and d omega, which is the energy per unit time carried by radiation with wavelengths d lambda across the area dAn, coming from the direction d omega. So, I omega lambda depends on the direction and wavelength of the radiation. Before moving on with the other radiation quantities, let's see what happens when radiation is emitted in gases, liquids, and solids. Let's first consider a volume of gas. Gas molecules freely move across this volume and there is usually a broad space between them. If the gas is not highly compressed, this behavior allows the radiations emitted by all the molecules to pass through this volume with few interactions and without being reabsorbed. On the contrary, molecules are much more closer to each other in liquids and solids, and only the radiation coming from the surface of a liquid or solid can escape without interaction or being reabsorbed. So emission is a volumetric phenomenon in gases, while it's a surface phenomenon in liquids and solids. We will discuss emission in gases later, but now let's concentrate on emission in liquids and solids. Let's consider an emitting surface. The power we would receive at an angle theta with respect to the normal of that surface is the spectral directional emissive power, which is the intensity of radiation times the cosine of theta. By integrating this value over the whole range of wavelengths, we obtain the directional total emissive power, which accounts for the overall spectrum of radiation. On the other hand, if we integrated the spectral directional emissive power over the whole hemisphere irradiated, we obtain the hemispherical spectral emissive power for a specific wavelength, or wavelength range, in case of isotropic diffuse radiation, which means that the intensity of radiation is independent on direction. The expression of the hemispherical spectral emissive power can be simplified to pi times the intensity of radiation for a single wavelength. Finally, by integrating over the whole spectrum and the whole hemisphere, we obtain the hemispherical total emissive power, which is the overall power emission of the surface. And again, if the radiation is isotropic and diffuse, the hemispherical total emissive power can be expressed as pi times the hemispherical total intensity of radiation. Similarly, if we consider a radiation incident on a surface, we can obtain the irradiance-related quantities. The spectral directional irradiance is the intensity of the incident radiation times the cosine of theta, which is the angle of incident radiation with respect to the normal of the surface. The directional total irradiance is obtained by integrating such quantity on the overall wavelengths range, while the hemispherical spectral irradiance is obtained by integrating it over the solid angle corresponding to the hemisphere lying on the surface, and, by combining those integrals, we obtain the hemispherical total irradiance. Irradiated bodies can interact differently with radiation, depending on their transparency, or opacity. In non-opaque bodies, which also include transparent bodies, the incident radiation can be reflected, absorbed and transmitted, and, due to the conservation of energy, the input energy, carried by the incident radiation, is equal to the sum of the reflected, absorbed, and transmitted energies. In opaque bodies, radiation cannot be transmitted, so the energy corresponding to the transmitted radiation can be considered to be null. And the energy balance becomes irradiated energy equals reflected energy plus absorbed energy. We can define useful material properties, which determine how different materials interact with radiation. Reflectivity if the fraction of irradiated energy which is reflected by the body. Similarly, absorptivity and transmissivity are the fractions of absorbed and transmitted energies, which are absorbed or transmitted by the body, depending on the kind of irradiance they are referred to. These properties can be directional spectral, directional total, hemispherical spectral, or hemispherical total properties. Reflectivity, absorptivity and transmissivity depend on material and surface properties. Also, keep in mind that a body can be opaque to all radiation. Radiation coming from a certain direction, or radiation of a certain wavelength. So, remember that in these cases, the corresponding transmittance is null. When a body is irradiated, the total radiation coming from it has two components: the radiation it reflects, and the radiation it emits, which is due to that body's own temperature. This total radiation is called radiosity, and it can depend on the radiation's direction and wavelength. The overall radiosity, integrated over the whole wavelength range and all the possible directions, is the hemispherical total radiosity, and it is defined as the sum of the emitted and reflected radiation. Through irradiance, reflection and emission, a body receives and loses energy, so it is useful to define the net radiative flux, which is the net radiation coming from that body. The net radiative flux is defined as the radiosity minus the irradiance, and it is measured in watts over square meter. The net radiation emitted by the whole body is the net radiative flux multiplied by the body's surface area, and is thus measured in watts. Previously we have defined the radiation quantities. But how do we measure them? We can help ourselves by defining an ideal radiator that we can compare to real objects to measure their intensity of radiation. Such ideal radiator can be defined as a perfect absorber, for which all its absorptivities are equal to 1. Having this property means that an ideal absorber can absorb all the radiation it receives, which would make it appear black. For this reason, an ideal absorber is also called a black body. This choice of ideal radiator is particularly useful because we can assemble a real object which, in practice, well approximates the behavior of a black body. It can be constructed as a spherical cavity with a very small hole on its surface. As shown in the bottom left figure, a spherical cavity with a very small hole can absorb, or trap, almost all the radiation that gets inside it. And, if the body temperature is higher than 0 kelvins, the body can emit radiation, which is able to escape the hole. Now that we know that the radiation coming from a black body is only emitted radiation, we can calculate its emissive power. The spectral distribution of the emissive power of a black body, at a given temperature, is described by the Planck's law. As the plot on the left shows, the emissive power of a black body has a peak at a progressively small wavelength as the temperature of the body increases. As you may remember from the beginning of this course, the wavelength corresponding to this emissive power peak depends on the body temperature. According to the Wien's displacement law, in fact, Wien's displacement law is derived from Planck's law. By setting the derivative of the spectral emissive power with respect to the wavelength to 0. Now, if we want to find the overall emissive power of a black body, we have to integrate its spectral emissive power over the whole wavelength's range. The resulting emissive power is the product of a constant, sigma, and the body's temperature raised to the fourth power. The constant sigma is called the Stefan-Boltzmann constant. For practical purposes, it is useful to introduce another quantity, the emission fraction. Emission fraction is defined as the fraction of power emitted up to a certain wavelength lambda, and the whole power emitted by a body. As you can see from the demonstration in this slide, emission fraction is a function of the product of temperature and wavelength. Two things should be noted about this function. 1. Let lambda p be the wavelength corresponding to maximum emissive power. The emission fraction from 0 to lambda p is 1/4. 2. For lambda t equal to 17,000 micrometers Kelvin, the emission fraction is 0.98 and it is usually approximated to 1. Which means that the whole emissive power is considered. We can now determine the emissive power of real bodies by taking the emissive power of a black body as a reference. For a real body, we define spectral directional emissivity as the ratio of the spectral directional emissive power of a body and that of a black body at the same temperature. Similarly, the total directional emissivity, the hemispherical spectral emissivity, and the hemispherical total emissivity can be defined considering their respective emissive powers. Let's look at some particular cases. Diffuse surfaces are surfaces the emissive power of which does not depend on direction. For such surfaces, the spectral directional emissivity is equal to the hemispherical spectral emissivity, and the total directional emissivity is equal to the hemispherical total emissivity. Real surfaces are usually not diffuse, but for engineering purposes and depending on the application, they can be approximated as such with little error. Moreover, if the emissive power of a surface does not depend on wavelength either, all the emissivities of that surface are equal. So far we used a black body, which is a perfect absorber, as a reference to measure emission of real bodies. But why use a perfect absorber to measure emission? The answer stands in Kirchhoff's theorem, which states that, for any surface emitting thermally stimulated radiation, the directional spectral emissivity is equal to the directional spectral absorptivity. This means that, since the directional spectral absorptivity of a black body is equal to 1, its directional spectral emissivity is also equal to 1, which makes it a perfect emitter, or perfect radiator. The Kirchhoff's theorem has also other important consequences. Since directional spectral emissivity is a surface property, directional spectral absorptivity is a surface property too. This means that their values depend on surface material and surface finishing. As we saw in the previous slide, diffuse surfaces have directional spectral emissivity, epsilon omega lambda, equal to hemispherical spectral emissivity, epsilon lambda, as they emit radiation with intensity which does not depend on direction. Due to this property, diffuse surfaces have also directional spectral absorptivity, alpha omega lambda, equal to hemispherical spectral absorptivity, alpha lambda, which is also equal epsilon lambda, which is equal to epsilon omega lambda. The same holds true for diffuse irradiance. Irradiance which does not depend on direction, which implies that alpha omega lambda is equal to alpha lambda. Gray bodies are bodies with uniform spectral properties, which means that their properties do not depend on radiation wavelength. So, for gray bodies, the hemispherical total irradiance, alpha, is equal to alpha lambda n to epsilon lambda, which is also equal to the hemispherical total emissivity, epsilon. The same equality holds true also when a body is in thermal equilibrium with a black body. But this is a very rare and impractical case. There is a particular kind of surfaces, which have uniform spectral properties for different wavelength ranges. Usually these surfaces have cutoff wavelengths at which emissivity and absorptivity abruptly change, and their behavior can be approximated with step functions. These surfaces are called gray band surfaces. They behave like gray bodies only when the spectral content of emission is very similar to that of irradiance. To understand why these surface properties are important, let's see a practical example. Let's consider a flat solar collector, which is made of a very dark plate exposed to the sun, usually protected by a layer of glass to avoid heat losses. And a heat transfer fluid brings the heat from the plate to some utilities. The temperature of the surface of the sun is about 5,800 kelvins, while the temperature of the collector's plate is 323 kelvins. The collector's plate has a cutoff wavelength of 3 micrometers, and has alpha lambda and epsilon lambda equal to 0.9 for wavelengths up to the cutoff wavelength, and 0.1 for bigger wavelength values. Let's determine alpha and epsilon. We can apply the definition of hemispherical total absorptivity to find alpha. It is equal to the integral over the whole wavelengths range of alpha lambda times g lambda over the same integral of g lambda only. Due to the surface properties of the collector, the numerator can be split into two parts. Alpha lambda is constant and equal to 0.9 for wavelengths up to lambda c, and it is equal to 0.1 for the remaining part of the integral. The sun can be approximated to a black body, so its irradiance can be approximated to the emission of a black body at the temperature of the sun. Substituting the expression of g lambda into the equation, we obtain that alpha is equal 0.9 times the emission fraction from 0 to lambda c, plus 0.1 times 1 minus the same emission fraction. The emission fraction in case of absorption is calculated with the cutoff wavelength and the temperature of the sun. The values of the emission fraction of a black body are usually reported in tables in textbooks. In these conditions, the value of emission fraction is almost 1. So alpha is almost 0.9. We can find the value of epsilon in a similar way, by applying the definition of hemispherical total emissivity. For the calculation of the emission fraction, we can still use the cutoff wavelength, but this time the temperature of the collector must be considered, which is much smaller than the temperature of the sun. In these conditions, the emission fraction is almost 0, so epsilon is almost equal to 0.1. As you just saw, the solar collector is built with a gray band surface to maximize absorption and minimize emission, which means to maximize energy collection and minimize energy loss. So far we have treated heat transfer between two surfaces. But what happens when multiple surfaces exchange heat with each other? Let's consider this system. Multiple surfaces exchange heat with each other in the surrounding environment. As shown in the figure on the left, the surrounding environment can be considered as a big surface, enclosing all other surfaces inside it. In this system, each surface is able to see only part of the other surfaces. So it is exposed to only part of the heat coming from those surfaces. Or it exposes the other surfaces to only part of the heat coming from it. As shown in the previous chapter, the heat coming from each surface is that surface's radiosity, which accounts for the emitted radiation and the reflected radiation. To express the heat exchanged between two generic surfaces I and K, we can then introduce the view factor, which is the fraction of heat coming from I which is received by K. Due to its definition, if we consider also the surrounding environment, the summation of all the view factors is 1 for each surface. To calculate the view factors for our system, we need to find the expression of the heat flow exchanged by the surfaces. Let's consider the figure on the left. The elementary surfaces dAI and dAj are separated by a distance r, and the elementary heat flow dQij travels within the solid angle d omega ji. From dAI to dAj, the expression of dQij is then directional total intensity of radiation times the cosine of theta I times dAI times dAj times the cosine of theta j over r squared. So, Qij can be found by integrating dQij over the surfaces AI and Aj. This integral is usually very hard to compute, as it strongly depends on the complexity of the geometries of the surfaces. But, luckily, textbooks usually report the pre-calculated values of view factors of many relevant geometries for engineering applications. Let's see some properties in particular cases of view factors. If a surface is diffuse, its intensity of radiation is independent from the direction, and it's equal to Ji over pi. We can then bring it outside of the integral, and simplify it with Ji at the denominator. By doing so, we eliminate the dependency on the heat flux, and view factors depend only on the geometry of the surfaces. Moreover, we see that the value of the integral does not change with respect to the reference surface. This property of view factors for diffuse surfaces is called the reciprocity rule. Radiation coming from convex surfaces cannot interact with the same surface. So for a convex surface I, Fii is equal to 0. If we have a convex surface 1 enclosed in surface 2, F12 is equal to 1. Which means that all radiation coming from surface 1 will be received by surface 2. Finally, let's consider a composite surface J with K portions, all at the same temperature. The product Fij times Ai is equal to the summation of all the view factors Fijk times Ai. Moreover, if the composite surface is diffuse, we can apply the reciprocity rule, and the view factor Fji becomes the average of the view factors Fjki, weighted on the surface areas of all its portions. Now that we know how multiple surfaces exchange radiative heat with each other, we can define the net radiation rate for I as the net radiation coming from I, and it is expressed by the surface of I, Ai, times the difference of the radiosity and irradiance of I. We can then develop this expression by dividing it into two contributions: the overall heat coming from I, and the overall heat coming from J. For each couple of surfaces we can then define the net radiation exchange, which, as the name suggests, is the net radiative heat exchanged by those two surfaces. We can further express each radiative heat flow in terms of the surfaces involved, their view factors, and the radiosity of each surface. In case of diffuse surfaces, which is a very frequent case, we can also apply the reciprocity rule, and this allows us to express the net radiation rate for I as the summation in J of the surface AI times the view factor Fij times the difference Ji minus Jj. This expression we just found for diffuse surfaces allows us to devise a lumped parameter model, which we can use to represent radiative heat exchange. We can express each net radiation exchange between the surfaces I and J as the difference Ji minus Jj over Rij, where Rij is equal to 1 over AIFij, and is called space resistance. This representation system is equivalent to Ohm's law for electromagnetism, where a current intensity I is equal to the voltage difference delta V over the resistance R. With the lumped parameter model, just like in electromagnetism, we can represent our heat exchanging system as an equivalent circuit. Each node is a surface and each resistor represents the space resistance between two surfaces. Although this representation can help us solve radiative heat transfer problems, it lacks the possibility to represent the system in terms of temperature of the surfaces. If we want to obtain a model which allows us to calculate the surface temperatures, we need to develop further the expression of the net radiation rate. Irradiance is a complicated function as it depends on all the surfaces radiating heat to a surface. To simplify our model, we can then try to express the net radiation rate in terms of only one surface. From the definition of radiosity, the irradiance Gi can be expressed as Ji minus epsilon I times Ebi over rho I. By substituting this expression of Gi in the equation of the net radiation rate, we obtain an expression which can already be used to calculate the temperature of each surface. As we know, the expression of the emissive power of a black body is a function of temperature. Alternatively, if we know the temperature of a surface, this expression helps us find Qi or Ji, if one of them is known. However, we can elaborate this expression further when dealing with gray surfaces, for which 1 minus rho I is equal to alpha I, which is equal to epsilon I. Remember that we are dealing with radiative heat exchange between surfaces of solids and dense liquids, which are opaque, so the transmissivity for each body is 0. So, for gray surfaces we can express Qi as Ebi minus Ji over Ri, where Ri is 1 minus epsilon I over epsilon I times Ai, and is called surface resistance. As you can see from its expression, surface resistance depends only on surface properties. Now we have all we need to determine the temperatures and the heat flows in our radiative heat transfer system, and we can use the lumped parameter model to represent it with an equivalent circuit. Each body can be represented with two nodes, one representing the real body with its radiosity, and the other one representing a black body at the same temperature of the real body, while the resistances are the space resistances, which represent the space dividing the real bodies, and the surface resistances, which represent the distinction between the black bodies and the real bodies, and is determined by the real body's surface properties. So, we can use our equivalent circuit to set up a system of equations to solve our radiative heat transfer system. For each body, if Qi is known, we can use the expression of Qi in terms of radiosities and space resistances to find the radiosity of the body I, while, if Ti is known, we can use the surface properties of body I, reflectivity and emissivity, to find its radiosity, or, vice versa. If the radiosities are known, we can use this system of equations to find the net radiation rate, or the temperature of each body. Remember that, if body I is a gray body, we can use its surface resistance to simplify equation 2 in the system. Let's see some applications now. And let's start from two-body enclosures. We have a two-body enclosure when a smaller body, body 1, is contained inside a larger one, body 2, as shown in the figure on the left. For such system, Q1, which is equal to minus Q2, is equal to sigma times the difference of T1 to the power of 4 and T2 to the power of 4 over the summation of the surface resistances of the two bodies and the space resistance between them. If the smaller body is convex, like in case B in the figure on the left, the expression of Q1 can be simplified because the view factor F12 is equal to 1. Furthermore, if body 2 is a black body, its emissivity is equal to 1, and the expression of Q1 becomes sigma times epsilon 1 times A1 times the difference of T1 to the power of 4 and T2 to the power of 4. The last formula is widely used for engineering applications of two-body enclosures, because it can also be applied when the area of the body 1 is much smaller than the area of body 2, even if the latter is not a black body, because its surface resistance becomes much smaller than the surface resistance of body 1. We can use the expression of Q1 we just obtained to linearize the equation of heat exchange between the two surfaces in a two-body enclosure. By using the properties of differences of squares, we can express Q1 as A1 times h rad times the difference T1 minus T2, where h rad is a pseudo-linear heat exchange coefficient, as it is equal to sigma times epsilon 1 times the sum T1 squared plus T2 squared times the sum T1 plus T2, and is thus a nonlinear coefficient. However, we can obtain a linearization of the heat exchange equation by considering h rad constant. This gives us an accurate approximation only when the value of T1 is close to T2. To have a more accurate linearization, we can use a first-order expansion in Taylor's series. In this way, we obtain another pseudo-linear coefficient, h rad star, which is equal to 4 sigma epsilon 1 times T2 squared. This gives us only a slightly better approximation of the heat exchange equation, and it can be used only when computing rough estimations. Let's look at another application, the Dewar flask. A Dewar flask is a device that allows to create an insulated chamber, usually of small size, thus called flask. The insulated chamber is made of two radiation shields forming a hollow space, with vacuum between them. Radiation shields are highly reflective surfaces, such as polished silver, so insulation is provided by radiation shields, which do not allow radiation to escape the flask, and vacuum, which does not allow heat exchange by conduction or convection. To keep the flask insulated, the internal chamber is then closed with a cork made with an insulating material. A common application of Dewar flasks is the thermos, which is used to keep liquids hot or cold for long times. But beware, radiation shields are not diffuse surfaces, so many of the simplifications and approximations discussed so far won't work for radiation shields. Let's look at one last application for this chapter. Three-body enclosures. As the name suggests, they consist of three bodies exchanging heat with each other. Like in the scheme in the figure above, if one of the surfaces, for example surface 3, is adiabatic, then there is no heat flow passing through it, while its surface resistance is still not null. This means that the radiosity J3 is equal to sigma times T3 to the fourth power, and that Q13 is equal to Q32, which means that all the heat sent from surface 1 to 3 is sent from surface 3 to 2. Adiabatic surfaces in such configurations are called re-radiating, or refractory surfaces, and are often employed in ovens and reactors for heating purposes. So far we have discussed radiation as a surface phenomenon, as we were dealing with solids and liquids. But, if you recall from the first chapter of this course, when dealing with gases, radiation becomes a volumetric phenomenon. This is because gas molecules are usually not tightly packed together, and this allows radiation to pass through volumes of gas, even of large amplitude. So, in this chapter we will discuss radiation emission and propagation in gases. Gases, like solids and liquids, can emit radiation. Moreover, gases and particles suspended in it can interact with radiation in different ways. Some gases, such as greenhouse gases like water, carbon dioxide and methane, are capable of absorbing radiation. When interacting with gas molecules, or particles suspended in a gas, radiation is also scattered, and scattering can be distinguished in two kinds. Rayleigh scattering occurs when the wavelength of radiation is much smaller than the characteristic dimension of the particle or molecule it interacts with. This kind of interaction diffusely reflects the incoming radiation. On the other hand, Mie scattering occurs when the wavelength of radiation and the characteristic dimension of the particle are similar. In these conditions, the reflection of radiation is strongly directional. Gas interactions with radiation significantly increase the complexity of heat exchange systems, but luckily we can use the following model to help us. Let's consider a slice of gas of length L, traversed by a radiation of initial intensity I lambda 0. Due to interactions with this slice of gas, radiation will decrease in intensity up to I lambda L at the end of the gas layer. So, considering an infinitesimal slice of the gas layer of thickness dx, the incoming radiation will have intensity I lambda x, while the outcoming radiation will have an intensity I lambda x plus dx. According to a model developed by Bugger, I lambda x plus dx is equal to I lambda x minus beta lambda times rho times I lambda x times dx, where beta lambda is called mass attenuation coefficient, and it takes into account the nature of interaction between radiation and the gas considered, and rho is the density of the gas. If we combine this expression with the Taylor's first-order approximation of I lambda x plus dx, we obtain that di lambda x is equal to minus beta lambda rho I lambda x dx. By integrating this expression, we obtain the Beer-Lambert law, which states that the gas transmissivity, or I lambda L over I lambda 0, is equal to the exponential of minus beta lambda rho L, where beta lambda rho L is called optical depth of the gas, which, among other things, depends also on the gas layer thickness. Therefore, the interactions with the gas increase at increasing gas layer thickness. In many engineering applications with thin gas slices, the effects of scattering can be neglected. In such applications we can write the expression of absorptivity as alpha lambda equal to 1 minus tau lambda, which is equal to 1 minus the exponential of minus rho beta lambda L. But how about emission? Do determine the emissivity of gases. Let's consider an elementary gas in thermal equilibrium with a hypothetical black body. For an incident radiation I lambda b coming from the black body, the gas will absorb and emit radiation of intensity rho beta lambda I lambda b dx. To keep thermal equilibrium, we can add the emission component to the Bugger's model that we saw before. By integrating and rearranging the obtained expression, we obtain the transfer equation, which takes into account also the emitted radiation coming out from a gas layer. By observing the transfer equation, we can see that epsilon lambda, which is equal to 1 minus the exponential of minus rho beta lambda L, has the same expression of alpha lambda. So, we can conclude that the Kirchhoff's theorem holds for gases too. Let's apply what we learnt so far to furnaces. And we will start from an ideal case. Furnaces burn fuels to produce high-temperature gases which exchange heat with the furnace walls. Let's concentrate on the radiative heat exchange. When furnaces burn hydrocarbons, the combustion process produces water vapor and CO2, which are the two main gases capable of absorbing and emitting radiation. However, for simplicity, let's first consider a single absorbing and emitting species A. The optical depth of this gas is ρ beta lambda L, where beta lambda depends on the radiation wavelength, gas pressure and temperature, and the partial pressure of the emitting or absorbing species. A model that describes particularly well absorption and emission of water vapor. Simplifies beta lambda as a function of wavelength, pressure and temperature, which is called modified attenuation coefficient, that multiplies the partial pressure of the considered gas. We can then plug in this expression in the formula for the calculation of alpha lambda and epsilon lambda. For our idle case, let's consider a hemispherical furnace, with its wall capable of absorbing all the radiation coming from the gas. The wall of the furnace then can be approximated to a black body. By the way, usually this black body approximation can be applied to the walls of real furnaces too, as their walls are usually highly oxidized and have very high absorptivities. For such geometry, the characteristic length L is the radius of the hemisphere, and we can use it to calculate the hemispherical total emissivity of the gas and the hemispherical total absorptivity of the wall. Remember that, since the temperature of the gas, Tg, is usually much higher than the temperature of the wall, Tw, the values of epsilon g and alpha w will strongly differ. For such ideal case, we can then express the net heat flow from the gas to the furnace wall as AW. The surface of the furnace wall, times sigma, times the difference epsilon g Tg minus alpha w Tw. The ideal furnace model previously introduced is very simple, but can also be very inaccurate in real cases. We can adapt the previous model to real cases by applying some corrections. To account for the real furnace geometry, the characteristic length is calculated as 4 times the furnace volume over the wall surface area, and it is called average beam length. To fit experimental data, Hodel and Seraphim introduced correlations which express epsilon g and alpha w as functions of temperature, pressure, partial pressure of a gas species and the distance from the absorbing or emitting source. Moreover, there are usually more than one emitting or absorbing species. When two species are participating, like H2O and CO2 for combustion, epsilon and alpha can be expressed as the sum of the separate emissivities, or absorptivities, of the two species, plus a parameter delta epsilon or delta alpha, which takes into account the antagonist behavior of the two species, as one species can absorb the radiation emitted by the other one. Finally, if we have multiple gas species, the problem usually becomes too complex for an analytical solution. To conclude this course, let's take a quick look at atmospheric radiation. And let's start from atmosphere irradiance. So far we have assumed for the Sun to behave like a black body with a surface temperature of 5800 kelvins. The radiation coming from the Sun travels a very long distance before reaching the Earth's atmosphere, and when it reaches it, the incoming radiation has an intensity of 1368 watts per square meter. However, as you should know by now, the irradiance of the atmosphere also depends on the direction of radiation. So, even if the intensity of radiation coming from the Sun can be considered constant, the atmosphere irradiance is not uniform, and it decreases as the angle of incidence increases. The irradiance of the Earth's atmosphere due to the radiation coming from the Sun GS is expressed as F times CS times the cosine of theta, the angle of incidence, where F is a coefficient, varying from 0.97 to 1.03, which accounts for the Earth's orbit eccentricity, and CS is the maximum irradiance, corresponding to the Sun's radiation intensity, which occurs for theta equal to 0. Once the Sun's radiation enters the Earth's atmosphere, it starts being absorbed by mainly water vapor, CO2 and ozone. As you can see from the plot on the right, water vapor is the main responsible for radiation absorption. It absorbs over the whole radiation spectrum, and is responsible for an attenuation of the Sun's radiation. On the other hand, CO2 and ozone give smaller contributions. Ozone absorbs small wavelength radiation, up to 0.3 micrometers, while CO2 only absorbs radiation around 1.5, 2 and 2.5 micrometers. However, the radiation spectrum is only slightly modified, so the Sun's radiation on the Earth crust surface can still be considered as black body radiation. With good approximation, radiation is also scattered along its path through the atmosphere. So, the irradiance GS, inside the atmosphere, is the sum of direct irradiance and diffuse irradiance resulting from the radiation scattering. The contribution of these components to the overall irradiance strongly depends on weather conditions. For example, on a sunny day, diffuse irradiance could be only 10% of the overall irradiance, while on a cloudy day, it can reach even 90%. Finally, the Sun's radiation is also partially reflected by the Earth's atmosphere. We can model this phenomenon by considering the atmosphere as an emitting body. At a temperature T sky, the temperature T sky can be calculated with models. For example, one of the simplest models is the Swinbank approximation, which approximates T sky as 0.0552 times the ambient temperature raised to the power of 1.5. Moreover, the Earth's atmosphere receives radiation also from the Earth itself. Due to its own emission, the temperature of the Earth crust is approximately 290 kelvins, which, according to Wien's law, corresponds to an emission peak at about 10 micrometers. One notable effect is the greenhouse effect, which causes the radiation emitted from the Earth to be partially absorbed by mainly water vapor, CO2 and ozone. In particular, water vapor absorbs radiation over the whole radiation spectrum. CO2 absorbs radiation with wavelengths between 13 and 16 micrometers, and ozone at about 9 micrometers. Congratulations! You've reached the end of this course. If you liked this course and would like to see more of this content, please leave a like and subscribe to this channel.